The new section is entitled Negative Binomial Random Variables. Negative binomial random variables. I need to give some information about this random variable. Okay, it has to have independent trials. The probability of success is P, but once again, P can be at any extreme point. It can be 0, that means impossible to happen, and it can't be 1, where it's certain to happen. Because if P was 0, then you always have failure and never success. And if P was 1, you always have success but never failure. You have to have each. Okay, so now we will perform the trials until a total of R successes. We will stop exactly after R successes. Now, this is similar to the geometric one, where we stopped after the first success. Now we're going to stop after the rth success. Okay, maybe we talked earlier about the New York Mets winning their first game after game number 3. They won it on the 3rd game. What if now we say, how many games do the Mets have to play to win 10? Exactly 10. Okay. Let x equal a number of trials. Let x equal the number of trials necessary to have R successes. Maybe I should really change it to n. N successes. It's just a letter. Now, the probability that x is equal to n. Okay. Well, we know one thing. That last game has to be a win. Okay, that last game has to be a win. So you have game 1, game 2, game 3, up to game n-1, and then game n. That's, oh, okay, yeah. That's the, oh, excuse me. I'm going to keep it R. That was a big error on my part. You want R successes. Okay. So clearly, the last game is a success. So in here, we want a total of R successes in all, but here, that last game is a success. So we want R-1 successes. Okay, so we are going to have P to the R-1. Well, how many failures are we going to have? Well, so far, we have R-1 successes and 1 more. That is, we have R successes. Well, it took n games to have R successes. Now, if the letters bother you, pick numbers. 11 and 5. It took 11 games to have 5 successes. Well then, how many failures did you have? 11 minus 5. I don't care that it's 6. I care how we get to 6. 11 minus 5, or n minus r. You're going to have failure n minus r times. Now, when you multiply these three factors, two of them can be simplified. P to the r minus 1 times a p to the 1. The bases are the same. You keep it, you add the powers. R minus 1, put back the 1, that is add 1, you get r. Q, actually, I just need to leave some space here. I need to leave some space. P times Q to the n minus r. But now, there's one thing here that was different than from the hypergeometric. Actually, it really isn't different, and we'll need to talk about that. There's one thing, and I should have left space at the beginning as well, so let me insert my space. Because there's one thing we didn't include. The probability that x equals n. The one thing we didn't include is from n minus 1 places, games, we needed to choose r minus 1 successes. Okay, that is, the way we can win the r minus 1 games in n minus 1 games cannot just happen one way. But earlier, we wanted this nth game to be the first win. We wanted it to be the first win. That is, the first n minus 1 games were to be losers. So from n minus 1 games, you wanted to choose n minus 1 ways to pick all losers. And this is 1. If you chose to say from the n minus 1 losing games, you wanted to pick no winning games, it's still 1. It's still 1. It's still 1. And that's why we didn't put this combinatoric formula in the geometric one. Because the part that I'm writing now was just going to equal 1. Again, from the n minus 1 games, you want to pick r minus 1 failures. And that's how many ways you can do that. And I guess I should say that n can be 1 or 2 or 3, etc. So that's the formula for the negative binomial random variable. If you want r successes in the first n trials, where that last trial is going to be a success. We don't want to say, but you know what? We lost the next 10 games. Why don't we include that in our... Okay, let me be crystal clear. Suppose we want to know, we want to win 3 games. 3 games. Exactly 3 games. So, now, what I'm saying is the number of trials can be different. Suppose you win, you lose, you win, you lose, you lose, you win. Okay? So you can say after 6 games, it's a probability that you won 3 games. Well, you can calculate the probability of winning, losing, winning, losing, losing, winning. Or 3 out of 6. But what if you lose again? Now you can say 3 games out of 7. Or 3 games out of 8. Or 3 games out of 9. Because you keep losing. Even in what I wrote here, you only won 3 games. But the rule is you stop after you won that 3rd game. You don't include the fact that you lost the next 19 games. So whenever I say the chances, what's the probability you win 3 games or 11 games? You stop after you won that 3rd game or 11th game. Okay, let's do a problem. It's very similar to the geometric random variable. We'll do a couple of problems. Suppose you toss a fair coin. Toss a fair coin. What does fair mean in this case? Means the probability of heads is a half, the probability of tails is a half. You toss a coin 3 times. Okay. Find the probability that the first time you had a total of 10 heads is after 15 trials. Probability that the 10th head, this is probably a better way of saying it, the 10th head is on the 15th trial, or we'll call it toss. A toss is a trial. Okay. So, R is the number of successes you have, and 15 is N, the number of trials. And we know that the probability that X equals 15 took 15 tosses to get 10 heads. We know that the probability that X is N is N minus 1, choose R minus 1, times P to the R, times Q to the N minus R. Well, we know what N is. It's 15. So that's 15, and that's 15, and R is 10. R is 10. 10. 10. 15 minus 1 is 14. 10 minus 1 is 9. P is a half to the R, which is 10, times Q is the other half, and 15 minus 10 is 5. So it's 14 choose 9 times 1/2. Since we're multiplying and the bases are the same, you just add the exponents. We are multiplying and the bases are the same. There it is. 14 choose 9 times 1/2 to the 15th, which my calculator is giving me 0.0611. So all you do is you plug in N and R into the formula. And remember, it's not N choose R because we're leaving that last one to be a win. We're choosing R minus 1 from all but the last trial, from N minus 1 trials. Why do we have N minus 1 successes? Because we isolated that last success, which would have made R successes. Suppose now you have a bias coin. Or a bias coin. In this case, the probability of heads is 2/3. 2 out of 3 times you'll get a head, which means 1 out of 3 times you'll get a tail. What is the probability that the 7th head is on the 8th trial? The number of trials is N, the number of successes is R. So we want the probability that X is N. We know it's N minus 1. Choose R minus 1. P to the R, Q to the N minus R. So this is equal to, well, 8 minus 1 is 7. R is 7. 7 minus 1 is 6. 7 choose 6. The probability of heads is 2/3. That's P, and we raise it to the R, which is 6, times the probability of failure is 1 out of 3, and we want N minus R, or 1. Now, it turns out that 7 choose 6 is 1. So, you have 2 to the 6th divided by 3 to the 6th divided by another 3. 3 to the 7th. And I get 0.1366. No promises on the calculations I do at my calculator. But there it is. Okay, you really need to be able to get that far. That's the probability part. Calculation isn't really probability. It's calculator math. This completes the section on negative binomial random variables.